Welcome to the model answer video and commentary for the induction test. Mark out of 30. On the first page, identify these hazard symbols. So as part of your week 1 sheet of your induction, you did this, and so we have, this is kind of a harmful to humans, kind of in a long-term sort of way, so like a carcinogen, or don't eat it, swallow it, that sort of thing. So long-term health hazard, e.g. carcinogen. Next one, a bit better, easy to remember. Highly flammable. So not only flammable, wood's flammable, but a bottle of ethanol is highly flammable. Picture gives it away. Harmful to the environment. So things that get kind of accumulate in food chains or will poison plants and animals. This is a strange one. A little bit of a clue. It's got a circle in, or an O. So it's an oxidizing agent. So it will provide oxygen to a fuel, so it'll burn really easily. So oxidizing agent. And this is probably the most common symbol you'll see in the lab, which can be used for a range of things. We used to have some separate symbols for these, but these are like irritant or toxic, or things you should avoid getting in your skins or eyes, or harmful. So irritant or harmful. So you'll often see those on the common chemicals in the lab. Now we have some conversions. Convert 18 millimeters to micrometers. Well, there's 1,000 micrometers in a millimeter. So there's 18 millimeters. That's 18 times by 1,000 is 18,000. And we've got our micrometers symbol there. So I don't need to add any further units. Express 130,000 in standard form. So standard form, we are looking for answers that have a number between 1 and 10. So we need to get a number between 1 and 10, and that's going to be 1.3 in this case. And then times 10, and then how many times we move in the decimal place? We're moving it 1, 2, 3, 4, 5. So that's times 10 to the 5. What is 132 nanometers to 2 significant figures? So there's our first 2 significant figures, and we would round this up or down depending. So it's going to be 130 nanometers. Convert 237 micrometers to millimeters. Well, we're going the opposite to the first one now, so our answer will be a fraction of a millimeter, because there's 1,000 micrometers in a millimeter, then this will be smaller than a millimeter. So we are going to divide this by 1,000, and it'll be 0.237 millimeters. And express 0.1437 micrometers to 2 significant figures in suitable units. So 2 significant figures would be, if we were keeping it as micrometers, 2 significant figures would be that 0.14. Do we need to round it up or down? Well, we'd round that down there, so we wouldn't need to round it up. So our first suggestion might be 0.14 micrometers, or suitable units. Well, are they really suitable? 0 point. Would it be better to have a kind of an integer number of numbers? Well, possibly better if we write here and convert it into the next one down, so nanometers, because that will give, so there's 1,000 nanometers in a micrometer, so that will give 140 nanometers as a better suggestion for a suitable unit. You'd much rather work with the number 140 than 0.14. Question 3. Calculate the magnification of this photograph. Some problems here. The information it gives us is this tiny little bar with the scale on down there. And so it's telling us that's 1 micrometers. But all sorts of suggestions of, well, measure the whole thing and, do some strange calculations. I'm going to work with the information I've got. I have got this, which is the scale bar, and we're going to measure that, and that is, so the scale bar is 9 millimeters. Okay, and that is the image size. The actual size is 1 micrometer. So 1 micrometer is the actual size. And so we need to convert these into the same units. We can't use these in different units, and the easiest way is to convert my image into micrometers. So that's 9,000 micrometers for my image. So that's my image, that's my actual. And then how many actuals go into my image size? So my calculation would be my magnification is 9,000 divided by 1 in this case. So my image divided by my actual, and that's 9,000 times. It's not got any units, but we put times, fine, just to show its magnification. 2 marks for that. Over the page we have got a spirogyrocell at a magnification of times 90. Calculate the actual length of the cell indicated by the black line. Okay, so we have got the line, and this is the image size. We can put our ruler on there, and that is 45 millimeters. I'm not going to use centimeters because that quite often gets difficult to convert units, so 45 millimeters. We're asked to give the answer in micrometers, so I'm going to convert that to micrometers right away. So that's 45,000 micrometers. So my black line there, my image is 45,000 micrometers. But it tells us that the magnification is times 90. And so I could write this equation out. Now A equals I over M. But what we're really going is, in your head, my line is 45,000 micrometers or 45 millimeters. It's not really that big, it's 90 times smaller. So I'm going to divide it by 90. So my image of 45,000 divided by 90, and I'm going to need my calculator for this one. 45,000 divided by 90 is 500, and it wanted micrometers, so I'm going to write micrometers there. Question 4. In this investigation, we've got permeability and pigment leaking out, and we're measuring using a colorimeter. You've used a colorimeter in your induction, and we measured absorbance. And the units of absorbance, it says arbitrary units, and we've got different temperatures. Okay, it doesn't say what the units of temperature is, but I think we know what that's going to be. Let's plot Leanne's results on a graph. Well, we're going to have our independent variable. If I just draw a rough kind of sketch of what we're going to have. So every table that you ever meet is going to be a box, and down the left we're going to have our independent variable. On the right we're going to have our dependent variable, and we're going to put our units in, units, and then if we've got repeats we're going to have 1, 2, 3, and then our mean there, and I'm going to put lines down there, and then we've got our temperatures down there. Okay, so that's how we're going to organise that, but in a kind of neat way. You notice that the independent variable is on top of the temperatures that we're going to put in. This dependent variable covers this entire set of 1, 2, 3 mean. It's over the top, so we don't need to write the units out. So I'm going to do that slightly neater. I'm going to write temperature. So temperature, does it say actually what the temperature of? No, so we can't give any more information there. And the units, so we can just put slash and then the units, degree C. Our dependent variable is the absorbance. What units have we got there? It says arbitrary unit, which means that we're not really interested in the exact units. So arbitrary units. I've just written it out exactly like it is there. And then we have got 3 sets of results. So we have got result number 1, 2, 3. Okay, and we're going to absorbance was recorded, and we're going to make a mean for this. So there's our mean. So we're staying mean rather than average. Our temperatures are 25, 35, 45, 55 and 65. I'm going to now make this into my nice table. We prefer nice enclosed tables, so a box all the way around. So box all the way around. Then there's no confusion as to what should be where. Then so I'll separate our independent variable from our dependent variable there. Our dependent variable is there, and then we've actually got okay, and I'll put that over there. I'm going to separate our first set of results, second set of results, third set of results, and our mean. And then I'm actually also going to draw these lines in here just to make it really clear about what goes where. So a fully enclosed table, everything's really clear as to where it's going to be. And now I just need to put the data in the table. So for 25 our readings are 0.8 0.5, 0.13 and 0.26, 0.16, 0.34, 0.09. If you can't line these up with the decimal places, it looks really neat. Sometimes I struggle. 0.27, 0.21, 0.19, 1.37, 2.00, 0.49, and then 1 is 1.66. Now I knew I was going to screw that up. 1.66. That's because this is so scruffy. 2 is 2.00 and 1.94. In the end, you can see as long as I scrub that out and write it again properly, then we're all right. So you can make mistakes with these. As long as you cross it out and it's in the right box, that's fine. So we need to calculate means now. So we are calculating a mean. So we're going to add them up and divide them by 3. So 0.05 plus 0.13 plus 0.26 divided by 3. And there is a bit of a question as to how many decimal places I put this to. In biology, it's fine just to keep it to the same decimal place. So keep it to the same level of precision. And so I'm going to put 0.15 there. And so I don't want any recurring numbers or anything like that. I just want it all to two decimal places. And let's do the next one. 0.16 plus 0.34 plus 0.09 is 0.59 divided by 3 is 0.196. Again, two decimal places. Well, I'm going to have to round this up, so that's going to be 20. Next one, 0.27 plus 0.21 plus 0.19 is 0.67 divided by 3 is 0.22. Next one, 1.37 plus 2.00 plus 0.49 3.86 divided by 3 is 1.286. I'm going to round that up. 0.29. And the last one, 1.66 plus 2.00 plus 1.94 is 5.6 divided by 3 is 1.86 recurring, so that's going to be 1.87. So the marks for the table is, so how many marks? We've got 3 marks for all of that work there. So headings with units. All of the table to 2 decimal places. The means correctly calculated. And that's what you should have for that. And then we're going to plot them on a graph. Have I brought some graph? There we are, some graph paper. Okay. Rules for drawing the graph. We want to use at least half of the graph paper, so on both scales. We need all the kind of names of the axes with the units. Independent. Let's draw a little sketch here. So we're going to have our independent variable there, and units. We have our dependent variable there with units. This needs to be, that's my sheet of paper, at least half. It's got to be big enough. I don't want a pokey little graph in the corner. Then we want a nice regular scale going up here using the, using 1s, 2s, 5s or 10s, that sort of thing. We want numbers. We want numbers at these. We need a number at the origin here, whatever that is. It might not be 0. Your points are going to be correctly plotted with crosses, and then you would use a ruler to join the points dot to dot. Okay, so that's where we're going. That's where we're going with that, and no extrapolation. So this line here would go there, but if I don't want to do it any further like that because there isn't another point to go to, so we can't extrapolate off each end. So let's have a go at that. Temperature along the bottom. So I want 25. So let's have a look. So if I went 25, 35, 45, 55, 65, that would be over half. So you're going to draw this in pencil. I'm going to be brave and draw it in pen just so it shows up on the video. I might screw this up, but it'll be clear on the video. Let's see if I screw it up or not. So that's going to be my temperature. My absorbance up the side. What scale? What's our biggest number there? Our biggest number, we're going to do the means, so it's going to be 1.87. So say if I went up in 0.24688, 10, 0.2468, that's going to be enough there. So I'm happy with this scale. So there we are. Okay. So my temperature, so this is going to be my temperature. Normally in biology they tell you what the exact temperature was of, so I've got temperature of the solution, temperature of, or the beetroot or whatever. And there's my units, degrees C. And I'm choosing to do 25, 35, 45, 55, 65. I could do this as 20, 30, 40, 50, 60 and so on, but it's still a regular scale. You could go 26, 27, 28, 29, so on. So it's still 10, 1 square per degree, so that's all right. This number here, what's this at the, what's this here? Well, this would be 45, 55, this would be 15. I haven't got any data for 15, but that would be 15. If I'm going to call it 0, I'd have to put a break in, which is equally fine. Up the side, this is our absorbance. So absorbance, and units is arbitrary units. And because this is close to 0, I'm going to start off at 0 there. And then I'm going to go up using these boxes here. So I decided to go up as 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, 1.8, 2.0. So I've got a nice regular scale. It's going up in a sensible division. So on this, 1 degrees is 1 square. I'm going up in 0.2s there. I've got numbers for my origin of the graph there. I'm going to be using more than half my graph paper. I've got titles and units. So we're so good so far. Apart from, this is not just the absorbance, this is the mean. I'm not plotting all this raw data. So that is actually the mean absorbance, isn't it? Okay. So now I can plot some points. 25 is 0.15 arbitrary units. So 25, so there's 0.15, so halfway between there. 35 is 0.2. 45 is 0.22. So that's 0.3. So that'd be 0.22 there. 55 is 0.29. So that's 0.3. That'll be halfway between those squares there. And 65. Oh, I knew I was going to make a mistake. My table. There's something wrong with my table, isn't there? 55 is wrong. It's 1. Is that 1.29? 1.37 plus 2.00 plus 0.49 plus divided by 3 is 1.29. So I'm crossing that out and writing 1 there, 1.29. So that means, oh no, that means my point now. I should have done it in pencil. 1.29, 1.2, there's 0.23, 0.29 there. Okay. Golden rule, use a pencil. And 65 is 1.87. So 1.8, that's 1.9, so that's 1.8 there. Okay. So joining these up, I'm going to do dot to dot using a ruler. So dot to dot using a ruler. I'm not going to do that point, my dove point. There. And hopefully I'm getting this from the centre of the point to the centre of the point. Okay, I can only go that far. I don't know where it's going to go after that. I can't draw this down to 0 here because I haven't got any data for that. So let's just double check everything. Axes are correct with units. My number, the origin is fine. I've plotted the points correctly eventually, and I've joined them with a ruled line dot to dot. Don't necessarily need a title in this case, but I could put one. So that's my graph for 4 marks. Describe the graph. So we need an overall. Let me get rid of my table. We need an overall trend. How many marks? We've got 2, and then we try and use some numbers or do any calculations or. So overall trend, as temperature increases, mean absorbance also increases. So as temperature increases, mean absorbance increases. Then we can talk about this relative increase. So we can say, slower increase between 25 and 45. Degrees C. A steeper increase or faster increase. Faster increase between 45 and 65. Degrees C. We could calculate a rate. So slower rate, we could triangle and calculate a rate, and the faster rate of increase between 45 and 65, or you could describe how many times. So